Okay, guys, welcome here. It is Thursday, April 23rd, and we are going to start our unit on equilibria. And our objective today is to be able to describe Le Chatelier's principle and how to write an equilibrium law. I'm going to give this one to you as quick as I can. Now, do all reactions happen in one direction? The answer to that is no. That is absolutely not true. We tend to think of reactions as simply going one way, but it's not true. They tend to go both forwards and backwards. Now, in the event of something like a combustion reaction, uh, things burning, you're lighting stuff on fire, they definitely pretty much roll one way. But reactions in solutions will tend to go backwards and forwards, and they will have a reversible part to them. And because of that, their conditions will change and their concentrations will change according to different stimulus. And that's what we're talking about with equilibrium. And here is a reaction at the top. We're going to be combining hydrogen and nitrogen to make a couple of ammonia molecules. What in the name of all things stupid is that? Okay, a couple of ammonia molecules. And notice that we start with a large concentration of our reactants. So here at the beginning, we've got all of our reactants, and we have no products. And this makes sense because the reaction hasn't started yet. So as the reaction goes, eventually, very quickly, it reaches this point, and this point is its equilibrium. And at the equilibrium, the concentrations no longer change. It doesn't mean the concentrations are equal, but it means the concentrations no longer change. It means whatever new product is being formed is equal to the amount of product that is coming back and becoming reactant again. So the forward and the reverse, up here, the forward and the reverse reactions are equal when it is at equilibrium. So what is equilibrium? It's when the rate of forward reaction is the same as the reverse reaction. So both reactions are running at the same pace at that point. Doesn't mean the concentrations are equal, but it means whatever's being made is equal to whatever is being unmade or going backwards. Now, what is dynamic equilibrium? Uh, for the overall system here, the same equilibrium constant is reached, whether you start from the forward or reverse direction. Go back. So it doesn't matter which side you start from. You'll still end up at equilibrium, whether you start from the product side or the reactant side, the forward or the backwards. Either way, you would end up in equilibrium. So from the example I just showed you, if we go back to this, if we had started with ammonia here, taking it apart, letting it decompose, we would still end up at the same equilibrium. And it is achieved no matter whether you start going forwards or backwards. Now, to write an equilibrium law, it would look like this. K, which we'll be using a lot here. K is just for constant. K will have no units on it, so that's a nice thing. On the top of it, we're going to have the products, their concentration, and then their coefficients, like this. And then on the bottom, we will have the reactants to their coefficients. And here we have more than one reactant. So what we'll have here for this reaction, K, will equal the concentration of hydrogen iodide, and that will be squared over the concentration of hydrogen to the concentration of the iodine. So this is an equilibrium law. That is how it is written, and there is no unit. And it is called an equilibrium law. And that's how we write it for the reaction. There's going to be a few things that we go into. We don't list solids or liquids because their concentrations can't change and will not affect our reaction. Now, with the Le Chatelier's idea here, we're going to try and stay at equilibrium. So if we add something, our system always tries to remove the stress of whatever's being added by removing it. So if we add A here, the system tries to produce more product to get rid of the A that we have added. The same thing if I take some, and I'm just going to change colors here for a second. If I take some A out of the system, so I remove A from the system tries to restore the concentration of A to what it is before. So it shifts the equilibrium over to restore the concentration of A. So our system is always going to try to restore equilibrium. So it's going to remove whatever we add to it. And if we remove something, it's going to try to replace it. So what does this look like? When stress is applied to a system at equilibrium, the system will readjust by shifting the equilibrium to relieve the effect of the stress. So if you add, don't do that. If you add reactant, it is going to try to remove the reactant by making product. That is simply the way that this thing works. And vice versa. If you add product, it is going to try to remove it by restoring the amount of reactant. So let's look at one example here. This is an exothermic reaction. We have heat on this side. We're going to try and treat energy exactly like it was any of the other reactants. So if we add it or we subtract it, it's just like adding or subtracting the sulfur trioxide or anything else. So if I were to add SO2 here, it would try to get rid of that SO2 by pushing equilibrium towards the product side. If I took sulfur trioxide out, it would try to restore the sulfur trioxide by producing more of it, by pushing equilibrium to that side to restore it. If I decrease the temperature, it would try to replace that temperature by pushing towards our product in this exothermic reaction. If I increase the volume, now this one is interesting. Take a look at the reaction here, and let's think about increasing the volume. Which side has more gas on it? Here I've got 2 and 1 more makes 3 gas on this side. I've only got 2 on this side. So if we increase the volume, it's going to want to keep the pressure constant. And so increasing the volume is going to favor the side with more gas on it. If I add the helium at a constant volume, this is one I think we'll just leave out this year. And I think we'll leave that out. And if we add a catalyst, adding a catalyst does not change anything. So all it does is speed the reaction. So there is no change. There's no delta if we add a catalyst. It isn't going to do anything to our reaction except speed it up. It's not going to change the concentrations because it's just going to reach equilibrium faster. All right, that's a pretty quick showdown of how this works. And we'll keep working at this. This I don't think is a one-day skill. So expect something akin to this tomorrow. Take a look at the answer solutions to Le Chatelier's homework that I gave you. I tried to give you a little bit of a push there and see if we could move forward on this. So tomorrow we'll do a little bit more on these equilibrium laws and talking about Le Chatelier's, and there's no way we're ready to calculate anything yet. Take care. Bye-bye.